So next, here, yeah, these questions we answered, and unbalanced production line with some machine failures, not all. So let us consider that scenario. So let me set this. Let me assign different numbers like cycle time 7 here, 9, and 12, 10, 12, 7, 9, 8. So let me generate the data for the 5,000 pieces and assign this inventory limit as 5 at every workstation. And regarding resources, what I will do is just remove this calendars also. So now we assign here for this second machine, I would assign failure rate 0.01 and fixed repeat time 25. And similarly, fourth one, 0.01, failure rate 25, fixed repeat time, and the same failure rate here, and 25. So I'm assuming that only these three machines are subject to failures and repairs, not all. And I'm considering unbalanced production line with no random variation. Okay, I'm going to simulate now. So let me create the jobs and go ahead and simulate. So here, the average daily production is 111. And for every almost 13 minutes, we are getting one piece. Okay, these are the statistics, and let me see the resource utilization, which I didn't show in the past for other examples. So you could see the resource utilization. This has a failure, so this is the total downtime during this period. Totally, we simulated for 64,689 minutes to make 5,000 pieces. And during that time, this R2 is not available. It has a repair time of 13,325 minutes, and this has a repair time of 12,750, and this one 14,110. You could see the utilization during this period. I know for what percentage of the time they are busy with pieces. You could see in this column. So it's very clear that the machine at a third workstation and machine at a fifth workstation are busy. Because you can see here, that is because the cycle time is 12 at a third and fifth workstations. That is the reason they look like bottlenecks. Now, if you want to make improvement, in productivity, you would like to do something at third and fifth workstations. For example, I want to reduce the cycle time by 20% here. Say make it 10 instead of 12. I reduce that cycle time to 10. That is reducing by 20%. And simulate this now. I would simulate this scenario. What I'm doing now, I reduced the cycle time at third workstation by 20%, that is 12 to 10, and simulate that. And I want to see the advantage of reducing that cycle time. I won't expect because there are two bottlenecks. Just improving at one bottleneck does not matter. So I should not expect much. So therefore, you could see this is not really big. This is very because of natural variation. Uh, you know, the random variation in failure times is a minor difference, but there's no change really. Similarly, instead of a third one, if I reduce the cycle time by 20% at the fifth one, and let me simulate now. So instead, I'm doing it at fifth workstation. I reduced that fifth station and seeing what impact it will have on productivity. So again, there is no change. So therefore, improving cycle time at third or fifth individually, no effect. But if I do both, there may be some effect. So let me reduce cycle time at third and fifth workstations by 20%. Okay. I forgot to generate. It reminded me to generate the data for new cycle times. So now I can see some improvement in productivity. So now, still not 101. I'm not sure that it did or not. Let me do one thing. Let me simulate once again with the 10, 10 at the fifth and third one. So 107. So I'm not getting much. No, even if I reduce cycle time by 20% at third and fifth one, I'm not gaining. The resource utilizations are still, now what's happening? All these three are bottlenecks. When I improved cycle time at third and fifth workstations, and now I see three bottlenecks. Now instead of what I will do, I will restore these cycle times as the original ones and create the jobs accordingly. And instead of any improvement third and fifth workstations, what I will do at fourth workstation, I will reduce the fixed repair time to 10 minutes instead of 25 minutes. So let me simulate this scenario. So now here I improved it to 117. This is significant difference from 111. I improved to 107 with one, by reducing the repair time at fourth workstation. I improved substantially compared to the reduction of cycle time at both workstation workstation 3 and 5 by 20%. But this is hidden. When somebody looks at this experiment, for example, here, this is the original, the first case in this scenario. Cycle time is 12 at third and fifth workstations, and these are the failure ones. And the daily production rate is 111. And then we improved that. Here we reduce it to 10. I think this is a. I think I didn't improve. 1 second now. What happened is I didn't. It is still saying that 12. All three 10. Okay. Let me consider this 10 and 10. I don't know why it didn't show. I go back and put 10 and 10. And here also 10. And create the jobs and go back and restore 25. I want to run that scenario. Okay, now the 10, 10, 10 I created the jobs. This also should give some improvement. But when I look at input and output, somehow I didn't put 10 for the fifth workstation. Here you could see this some better. But what I mean to say, when you look at this case, when you look at this case, the very high utilization these two, giving impression that they are bottleneck. This is not a bottleneck, but the real bottleneck is the fourth one. So when you improve cycle time, when you improve repair time, there is a major advantage, but that is hidden. So normally, when people go by common sense, they want to improve third and fifth workstations, but that's not effective in this case. So what I mean, sometimes there are hidden opportunities, improvement opportunities. They may not be visible. They are beyond our common sense. In such case, these Monte Carlo simulations is quite helpful. That's my point.